Okay, let us start. Can you see the screen now? The sketch is visible? Visible?
Yes, sir.
Okay, okay. Last class, we were discussing about how to determine mean precipitation for a given watershed. So in this respect, we have discussed three different methods. The three different methods which are available for us are the simple arithmetic average method, the second one, more accurate Thiessen polygon method, and also equally accurate third method, isoheitel method. And each one of them have their own pros and cons. The arithmetic method is a very simple method. The average value obtained by that is good enough for some coarse estimates, whereas when you need precise value of the average rainfall, we have to look for two other methods, either Thiessen polygon method or isoheitel method. As I said earlier, the Thiessen polygon method is the one which is adopted even in application softwares of today, because of the well-planned structure by which the process happens in this has made it easy for programming. Even isoheitel method is also a good procedure, but drawing isoheights would call for very good experienced hydrologists in order to get them proper, based on which finally to decide on average annual precipitation. Now, in that context, we have discussed one nominal example illustrating how calculations are done for each of these methods. Now we will look at another example which we had just started but did not complete. So this one, the sketch which is shown on the screen, represents a watershed. Now this watershed is represented in a regular geometric shape, which may not be the case actually. It is only for reasons of avoiding the hardship in determination of the area of the polygon. A well-defined geometry is suggested to understand the concept behind this Thiessen polygon method. So here, the statement of the problem last class we discussed, it is said that the figure is composed of a square of 10 kilometer side and an equilateral triangular plot of 10 kilometer side. The annual precipitation at rain gauge stations located at four corners of the square as well at the apex of the equilateral triangle are mentioned. So the rain gauge stations are at locations A, B, C, D, and at the center E, as well at the apex of the triangle F. So these are the values which are suggested in bracket: 46 centimeter, 65, 76. Likewise, for each of those cases, the values of the rainfall are also indicated. Now, using this, we have to determine mean precipitation by Thiessen polygon method. So just to review what needs to be done in Thiessen network is, first of all, we will know the location of each of the rain gauges. And here it is A, B, C, D, E, and F. And each of these rain gauge stations have to be joined by means of a dotted line as shown here to form triangles. Each of the rain gauge stations should be joined to each other by means of a dotted line to form triangles as shown here. The triangles for illustrations are triangle AEB, BED, DED, CED, AED. Likewise, you can join all of that and get various triangles within this particular watershed. Now, after that, for each of the sides of the triangle, we have to draw perpendicular bisectors as shown by solid lines here. A perpendicular bisector here is shown for the line AF. Similarly, a perpendicular bisector is shown for the line DF. Another perpendicular bisector for line AD is shown here. And when you produce them either forward or backward, they converge to a single point, that is point of concurrence. Here, these three perpendicular bisectors converge and meet at this point in this equilateral plot. Similarly, the various other locations where perpendicular bisectors meet are, this is another location. You have one more location here, one more, and one more. So these are the locations where all perpendicular bisectors would meet. Now, next step is to decide which polygon corresponds to which rain gauge station. For example, if you look into, just look at the cursor I am running through, see this part of the area. This is boundary, dotted line, and this is the polygon which we have drawn. So this triangle forms the area for rain gauge station B. Similarly, for rain gauge station C, this is the area under its jurisdiction for C. Similarly, if you take for D, the area under its jurisdiction is, you start from here, part of the square as well part of the equilateral triangle. Similarly, for A, it is part of the equilateral triangle and part of the square. So if you look into the symmetry of the sketch, the area under A and D are equal. The polygon area under A, the polygon area under D are equal. Similarly, the polygon area under B, the polygon area under C are equal. Then finally, you have one square within the bigger square here. This is the bigger square, which forms the polygon for station E at the center. Station E at the center. Similarly, going further, the area under station F is indicated, I run through the cursor, by this polygon. So based on this, we have to calculate the area under each of these polygons with reference to the corresponding rain gauge station. So if you look into this, so we can easily understand how it can happen. For example, if you look into this, see, I have done the calculation here. I will show you how to calculate this. Let me just take it to the Excel sheet first. So let me just do that for you and then come back to the calculation part. Just a minute. I will take everything to the Excel sheet here. 1 second. Let me expand this a bit such that everything is clearly visible. Now here, yeah. So here, the first thing, let me say, we have to take in the first column the various rain gauge stations A, B, C, D, E, and F. They are the one which we have shown in the sketch. Here, you look here, A, B, C, D, E, and F. So rain gauge stations are shown. Once you show the rain gauge stations, you take the corresponding values of the rainfall values in each of those locations, starting from 46. Suppose if you look into, so A has 46, B has 65, then 76. All values are tabulated here. So values are tabulated here till F. Then area in square kilometer. This is what I have calculated. I will show you how it can be done. For example, if you look into, first let us start with this B first of all. See, if you look into, by the concept of perpendicular bisection, this side AB is into two equal parts. So this side is 5 kilometer, and similarly the side BC is also with a perpendicular bisector, half this distance. Therefore, the sides of this triangle adjacent to this B is 5 kilometer by 5 kilometer. 5 kilometer width, 5 kilometer height. Therefore, based on which, if you take the area of the triangle, I will show you half base into height. Half base is 5 kilometer, height is 5 kilometer. It becomes 12.5 square kilometer. So that 12.5 square kilometer against B I have indicated. I have substituted 12.5 against B. Similarly, if you look at location C, it is also of equal area, half base into height, of 5 kilometer into 5 kilometer, 12.5. So for that also I have put 12.5 here. So B and C are done. Is this point clear to everyone? This is clear? Yeah, somebody please respond. Is it clear?
Yes, sir.
Calculation of the area? Yes?
Yes, sir.
Okay, okay. Then we will move further. Then we will go to next one. One second. Yeah, here. Area under B is known, area under C is known. And then the area under A is this triangle for which the area we already are aware of. That is same as that of B, that is 12.5. Plus it has an area from the equilateral triangle also. Plus you have the area from the equilateral triangle also. So equilateral triangle, because of these three perpendicular bisectors, is divided into three equal parts. These are three equal parts. Equilateral area is into three equal parts. Now, first of all, determine the area of the equilateral triangle. Suppose if you wish to determine the area of the equilateral triangle, the direct equation can be used, which is square root of 3 divided by 4 into side square. So suppose if you do that, I will show you square root of 3. The direct equation I am taking, square root of 3 into side square. Side square is 10 into 10. 10 kilometer into 10 divided by 4 will give you area of the equilateral triangle. This is 43.3. So directly you can get the area of the equilateral triangle. Once you have the area of the equilateral triangle, three parts to this. 1, 2, and 3. 1, 2, and 3. So you look here. Therefore, 1/3 of this area. So 1/3 of this is nothing but equal to this divided by 3. So each part of the equilateral triangle is 14.43 square kilometer. So that also you can understand from this. This is 14.43. This is 14.43. This is 14.43. Therefore, the area under A is the polygon area for A is this 12.5 plus 14.43. So that value will become the area under A. I will write that here is equal to 12.5. The area which is already determined here, right? So already determined plus this 14.43. So if we calculate that, it becomes 26.93. That is written here. The area under that is 26.93. That is how you will calculate. Similarly, whatever you calculate for A will remain for D. Area of the polygon for A and D are just the same. So if you look into the sketch, it is just the same. 26 point here, area under A, area under D. So this is the area. And for this is the area. So both are equal for A as well as D. That value I have substituted here. Whereas the remaining part is for F, that is 14.43, which we have calculated. 14.43. So this is how you can calculate. Suppose for some reason you don't remember the area of the equilateral triangle, root 3 by 4 into side square. If you don't remember that, the other way of doing it is also possible. You look into this possibility also. All these sides are of 10 kilometer, right? So then this perpendicular bisector is exactly at the center. What you can think of is this equilateral triangle can be a constitution of two right angle triangles, whereas the base being 5 kilometer, the hypotenuse being 10 kilometer. The height is not known. Then you know from the equation c square is equal to a square plus b square, based on which you can calculate the height of the equilateral triangle. So the height of the equilateral triangle If c square is equal to a square plus b square, then b square is equal to c square minus a square. So you can determine. Therefore, what you can do is that you can determine height of the equilateral triangle as square root of 10 square minus 5 square. So the height can be obtained. Once you have the height, then you look into this. Once you have the height of this, the base is 5, height is this, area of one right angle triangle can be taken. The area of equilateral triangle can be taken. So suppose if you calculate that, it is equal to half, base is 5, height is 8.6. This is one right angle triangle. Therefore, there are two right angle triangles in the equilateral triangle. Therefore, if you multiply that, this 43.3 and this 43.3 matches. You can use any equation you wish. Here I have directly used that and entered all values for the purpose. And finally, we have to decide the area under the station D. The area under the station D, if you look into. So here, this is a square cornered by 4 triangles, each of area 12.5. Therefore, the bigger square has an area of 10 by 10, 10 kilometer by 10 kilometer, 100 square kilometer. So you deduct 12.5 plus 12.5 plus 12.5 plus 12.5. You deduct 50 in all. 100 minus 50, 10 into 10 minus 4 into 12.5 will become 50. That is written here. Is this calculation clear to everyone? Is it clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Once this is done, the next thing is very easy. You take the sum of all these three. So that I have calculated here. Sum of all this, the add all of this, you take the sum. Just to check, I will show you once again here. Sum of all this is equal to, so I take the sum. In exam, you will use calculator, not Excel. 143.29. Look here, both of them match. 143.29 is the total area. Then you take another column where you multiply rainfall value with area. So these two are multiplied. 46 and 26.93 are multiplied. I will just show you whether it is the same one what I have calculated. So look here, 46 into 26.93. So you get 1238. Look here, both are similar. Once you do this, then you calculate for other rows also. See, look here, everything matches. 865, 3500. Likewise, you calculate for every situation. I will remove this. The calculations are correct. So now once you do this product, you take its sum also. So this sum, the sum of the products, sum of these products. And then finally, what you have to do is that you have to divide this product sum by the total area to get the mean value of the precipitation. Mean precipitation, if you wish to calculate, mean precipitation is equal to this 95.48 divided by 143.29, 66.45. So you can reduce this to 2 decimal locations so that the practical limits are also maintained proper in measurement. So 2 digits for which you have to take. So 66.45 is the average precipitation. That is what I have shown here, 66.45 centimeter. Is this clear to everyone?
Yes, sir.
Okay. Any doubt with this, please let me know. Any doubt? If you have any doubt, please let me know. I'll wait for a minute. Just in case if you have anything to ask, please let me know. Okay, shall we move ahead then? Okay.
Yes, sir.
Okay, we'll move ahead then. Now, the next one, next example. It is a similar example. What I would do is that what all we discussed for today, the various numericals, that is not part of the class notes which I have supplied to you. This I will mail it separately today after the class. You can have a look into this. The next example is also very much similar, but for 10 kilometers, here it is shown as 2 kilometers, 2 kilometer, 2 kilometer, 2, and rainfall values are also different, based on which the average precipitation is calculated. You can work out for yourself and check. This I will share with you. This I will share with you, so you can work out for yourself. Okay. Okay. Next one. I will move on to the next one. I will come to this Thiessen polygon method, where regular geometry of the watershed is not available. This does not possess regular geometry. If you look into this, the watershed is of irregular shape. The dotted line shown represents an irregular shape. And even the polygons are drawn as a part of the problem statement itself. You have got this. There are no lines joining shown here. The line joining various rain gauge stations and the triangle formation is not shown here. But whereas directly the polygons are drawn in the sketch and supplied to you for further calculation or computation. So here, each of the rain gauge stations have some value of the rainfall indicated. So you can see that by the side of the each rain gauge station, A, B, C, D, E, F, G, H, it is shown. And then polygons are also drawn. As a problem statement itself, the areas are also mentioned to you here. The areas are also given. The precipitation values you can directly take from each of these locations. 9.3 for A, 10.5 for B. Similarly for F, you can take 14.0. So likewise, you can take the values accordingly. Now the next step for average value of mean precipitation value, what you have to do is that in a similar way, you have the tabular column. Here, I will take this tabular column as it is. I will take the tabular column. In a similar way, you would do that. I will show you. So polygon area, look here. You have determined rainfall area, and then you have to take the product of these two. Product of these two is this column 2 multiplied by this column 3. So I will take the product of this 170 star 9.3. So similarly, you calculate for other locations too. So that also is done. Now you calculate the sum of the area, sum of the polygon. Sum you have to calculate. So you calculate the sum. So sum of the area is 958. In 10 minutes time, we may be cutting automatically the communication. You please rejoin immediately after that. In 5 minutes time, we will continue from there. So if this is 958, then the product sum also you calculate. That also I have done. And then the average precipitation value, here if you take the average precipitation value is equal to this value divided by 958. So you get this as 11.69. Is this point clear to everyone? This is clear? Mean precipitation is 11.69. Directly you can do that. So in this example, the task of what I would say, determination of the area after drawing the triangle network is reduced. Directly values are given for computation. So this is how you can easily obtain. Any doubt at this stage for this example? Any doubt for this? Somebody please?
No, sir.
Okay. Okay, this is clear, is it? So the details of this I will share with you in WhatsApp group. You can just have a look later. Just in case if you have any doubt, you can get it clarified in the next class. Then the third one, so isoheightal method. So here also we have all isoheights drawn. 6 centimeter isoheight, 8 centimeter isoheight, 6, 4. Likewise, we have all isoheights are drawn based on the rainfall values recorded at various rain gauge stations. And between two isoheights, zones are formed. So here, below 6 centimeter isoheight, you have zone 6. And between 6 and 8, you have zone 3. And then greater than 10 centimeter isoheight, this circular area is zone 5. The one between 10 and 8 centimeter isoheight is zone 4, which is indicated. Between 8 and 6, I already said it is third zone. So a big area, a chunk of the area, major chunk of the area, right? Then between 6 and 4 centimeter, zone 2. And for all values less than 4 centimeter, zone 1. But in cases of this isoheightal method, if a problem statement is of this kind, you have to understand one thing. The understanding is that this is 6 centimeter isoheight. This is 8 centimeter. You have to understand that to the right side of this 6 centimeter isoheight, rainfall value increases. Whereas to the left side of this 6 centimeter isoheight, it reduces. Similarly, this is 4 centimeter isoheight. This is 6 centimeter isoheight. So to the left of 4 centimeter isoheight in this direction, in zone 2, the rainfall value increases. Whereas to the right side, entering zone 1, the value of the rainfall reduces. Then come back to this zone 5. It is surrounded by 10 centimeter isoheight. And the next isoheight outward is 8 centimeter. Therefore, from 10 to 8, it reduces. Whereas towards the center of this isoheight, the circular area, towards center of the circular area, the value of the rainfall will increase. This is the understanding you need to have. Unless you have this understanding, the tabulation of the values and determination of mean precipitation between isoheights can be slightly confusing. So first of all, you have to understand this. This dotted line represents the boundary of the watershed. Next, we have the locations of the rain gauge stations with values of the rainfall indicated. And then an experienced hydrologist will sit and interpolate all values and would draw these isoheights. Isoheights are nothing but the locus of points of equal rainfall. Once these isoheights are drawn, then zones are marked as zone 1, zone 2, zone 3, 4, 5, and 6. And then the area of each of the zone is calculated. That determination can happen either by planimeter or by graph sheet or transparent graph sheet, looking into the scale which we have used for plotting this diagram. And in this example, directly the values of the area against each zone is mentioned to us. It is directly mentioned to us. And the values of the rainfall is also indicated in the sketch against each of the rain gauge stations, values of the rainfall, and because of which the values of the ISO heights are also known to us. So how are we going to solve this kind of problem? So here, in order to solve this kind of problem, first of all, what you have to do is that first you take these zones as it is. First of all, I will take this as it is onto the Excel sheet. See, I have taken zone 1, zone 2, zone 3, zone 4, zone 5. So now the ISO heights for these zones have to be understood. Suppose if you take the first one, zone 1, if you look into zone 1, this is zone 1. Zone 1 is to the right side of 4 centimeter ISO height. Right side of 4 centimeter ISO height. And the value of the rainfall reduces in this direction. And also look for intervals of the ISO heights which are shown in the sketch. The intervals you can easily understand from 4 centimeter, 6 centimeter ISO height, 8 centimeter ISO height, 10 centimeter ISO height. Means that the ISO height intervals are taken as 2 centimeter. Therefore, this zone 1 can be considered as an area between two ISO heights of values 4 centimeter and another ISO height to the right side of this 4, that is 2 centimeter. It is between an ISO height of 2 to 4 centimeter. Is this point clear to everyone? This is very important. Zone 1 is between an ISO height of 2 centimeter and 4 centimeter. Is this point clear? Some assumption or some understanding from the sketch has to happen. This point is clear? Yes or no? Clear?
Yes, sir.
Okay, clear. Therefore, I would write that here in ISO heights. ISO heights, it is between 2 to 6 centimeter. 2 to 6 centimeter ISO height. I'm not writing the units here. Anyway, I will share the content. 1 second. 2 centimeter to, I will write it very clear. 6 centimeter ISO height. Then next one, zone 2. It is already shown in the sketch, very clear, 4 to 6. 4 centimeter to 4 to 6 centimeter, zone 2. Then zone 3, 6 to 8. Zone 3, 6 to 8. Zone 4, 8 to 10. 8 to 10. Zone 5, 10 to 12. See, you have to understand, within that circular area towards the center, it increases. So therefore, you can take it as 10 to 12. And the last one, zone 6. To the left side of 6 centimeter, it reduces. Therefore, it is between 4 to 6. And as well, the rain gauge station indicates 5.56 is here. You can easily understand that this is between 4 to 6. So this is something what you have to do. Then you have to calculate the average value of the precipitation. The average value of the precipitation needs to be calculated. So average precipitation, if you take